Hello everyone, welcome to my YouTube channel. Today we're going to discuss the Cambridge International AS and A level, which is paper 21. The subject code is 9701, May-June 2023. This paper contains 60 marks paper. Let's start from question number one. Before starting question number one, don't forget to subscribe my channel. Okay, now this question is about the tellurium is an element in group 16. The most common isotope of the tellurium is Te130. Its electronic configuration is, this is the noble gas electronic configuration of tellurium. This is a krypton, then 4d10, 5s2, and 5p4. So complete the table. Tellurium is 130. So if you look at the periodic table, the proton number of the tellurium is 52. Then nucleon number, this is the nucleon number. 130 is the nucleon number. Number of neutrons, number of electrons. Okay, 52 is the proton numbers. This is atom, so that's why it must contain 52 electrons. The number of neutrons, 130 minus 52, which is 78. So there are 78 neutrons in tellurium atom. Identify the subshell in an atom of Te that contains the electrons with the lowest energy. If we look at the electronic configuration, as the rest of the electronic configuration is there. So if we start our electronic configuration, it starts from 1s, then 2s, then 2p, then 3s, then 3p. So the energy of orbitals that increases from left to right. So this is the lowest energy orbital in which the first two electrons of tellurium are there. So this is 1s. Construct an equation to represent the first ionization energy of tellurium. Ionization energy is the minimum amount of energy which is required to remove 1 mole of electron from the 1 mole of gaseous atom to make 1 mole of gaseous 1 positive cation. So the atom and the cation must be in the gaseous form. Then the radius of tellurium ions decreases after each successive ionization. State two factors that are responsible for increase in the first 6 ionization energies of tellurium. If you look at the electronic configuration, the outermost electrons are present in 5s2 and then 5p4, and the principal quantum number is 5. So they are present in the fifth shell, and if you add these two electrons, there are 6 electrons in the outermost shell of tellurium. So there must be a rapid rise between 6 and 7, but we have to explain the two factors that are responsible for increasing the first 6 ionization energies. I mean, if we remove the first electron, then the second electron, then the third one. So at every step, the ionization energy decreases. Actually, the nuclear attraction, they will start increasing. I mean, the nuclear charge become more effective. So we can say the nuclear charge becomes more effective. I mean, if it becomes more effective, then there must be an increased nuclear attraction. And then there is a decrease in shielding of subshells. At first of all, we have to remove the electrons from the 5p and the p subshell that contains 3 orbital, and then we have to remove the electron from 4s. This is 4s. This is for p. So for 5p. So 5p contains 4 electrons, 1, 2, 3, and then 4. And 4s contains 2 electrons. So if we remove the 1 electron, that is easy because there is an electron spin repulsion. So we can remove this electron. Then the more stable orbital will be there, the second electron, then third electron, then fourth electron. Then there must be a rapid jump, a little bit jump between 4 and fifth ionization energy as well. So when we move from left to right, the nuclear charge become more effective. Nuclear attraction, they will start increasing and decrease in the shielding of subshells. As when we remove all the 4 electrons, then we have to remove the electron from the 4s. Then we can say that there is a electron spin repulsion. So electron spin repulsion is there. Okay, then sketch the graph. Show the trend in the first 7 ionization energies of the tellurium. So the electrons are present, 6 electrons are present in the outermost shell. So there must be a rapid rise between 6 and 7 ionization energy. Then first electron, then second electron, then third electron, and then fourth electron, and then fifth electron. So mm, this is fifth electron. I have explained that if we remove the fifth electron, that must be removed from the 4s. So that's why there is a, a little bit increase from the ionization of fourth and fifth. So this is the first, then second, then third, then fourth, and then fifth, and then sixth, and then is a rapid rise in the ionization energy of 6 and 7. So it means that the now the 7th electron must be removed from the previous principal quantum number shell. So Te reacts with F2 at this temperature to form this. Okay. Now the octahedral shape. Explain why TeFx is okay. Te has 6 electrons, so 1, 2, 3, 4, 5, 6. So if 6x are attached, we will get a structure like this. It means that Te do not have any lone pair. So it has no lone pair, but it has 6 bond pairs. No lone pair, but 6 bond pairs. So that's why the orbitals repel each other and fix fixed at a minimum repulsion. Then we will get the octahedral shape. Then the TeF6 reacts with water to form tellurium hydroxide and HF. The oxidation number of tellurium does not change during this reaction. Construct an equation for the reaction of TeFx with water. We know that whenever we have an octahedral shape, then the formula must be XF6. So we can write like the TeF6. Okay, so react to the water. Yes, okay. This is water, and then it will form Te, because the oxidation state of Te is +6. So it will form TeOH 6 times, and then we will get a HF as well. So HF. So if we balance this chemical equation, 6, okay, here, so we can put 6 and then 6, so 6, 6, 12, the rest of the equation is balanced. Name the type of reaction that occurs when TeF6 reacts with the water. This reaction is hydrolysis. So this is the first question of this paper. Second question, a neutralization reaction occurs when sodium hydroxide is added to sulfuric acid. This is a reaction between sodium hydroxide and sulfuric acid, a neutralization reaction. Uh, Define enthalpy change of neutralization. Enthalpy change of neutralization is the enthalpy change when 1 mole of water is formed. The enthalpy change when 1 mole of water is formed from aqueous solution of an acid and base or alkali. Then an experiment is carried out to calculate the delta H neutralization for the reaction between sodium hydroxide and sulfuric acid. 100 centimeter cube of 1.0 mole per dm cube sodium hydroxide is added to 75 centimeter cube of 1.0 mole per dm cube sulfuric acid in a polystyrene cup and stirred. Then results from an experiment are shown in the table. Initial temperature, then initial temperature of both these reactants. So if we take the average, then we will get the same thing. We will get the 20. So if they have the different temperature, then you can take the average. Maximum temperature rise, that is the 27.8. So initial temperature was 20 and the maximum temperature was 27.8. It means this is the exothermic reaction. Use equation 1 to calculate the amount in moles of sulfuric acid that is neutralized in the experiment. So if we look at the moles of sodium hydroxide, so first of all, moles of sodium hydroxides are 1.0 times 100 divided by 1000. So there are 0.100 moles of sodium hydroxide. If we look at the reaction, that happens with 2:1. So 2 moles of sodium hydroxide can neutralize 1 mole of sulfuric acid. So if we want to find out the moles of sulfuric acid, just make it half, then you will get the moles of sulfuric acid. So moles of sulfuric acid neutralized, they are 0.0500. Although sulfuric acid has its own data, like 75 centimeter cube of 1.0 mole per dm cube, we can also find the moles in this, but the sulfuric acid is an axis. So he's asking about the moles of sulfuric acid that is neutralized. So this much amount is neutralized, and we can find the moles of this. And if we subtract the moles, that is actually the moles left behind in the solution. Now, delta H neutralization using the results table 2.1 include units in your answer. So the specific heat capacity is given. Then there is assumption that 1 centimeter cube is 1 gram, no heat loss, full dissociation of sulfuric acid. The experiment takes place at constant pressure. Show you working. So we have to calculate the enthalpy change. So first of all, let's calculate the heat transfer. So heat transfer Q is equal to negative MC delta T. We can put the MC delta T, then we can put a negative sign at the end, or negative MC delta T, because we know that this is a reaction. This reaction is exothermic, so negative. And the neutralization, we have to add the volumes of both the acid and bases, 75 and then 100. So we have 75 for one substance plus 100 for the second, multiplied by 4.18 times temperature is 27 was the final, 27.8 minus 20.0. So if we multiply this, we will get we'll get minus 5705.7. Now the units are joule because mass is in grams. Then multiplied by this is specific heat capacity is in joules per gram per Kelvin. And if you take the difference of temperature, that is in Kelvin. So Kelvin, Kelvin, you can cross this, grams, grams, and you will get the answer in joules. So you can convert it into kilojoules as well, or you can use the same answer as well. That because there are not specific units out there. So if we divide by 1,000, you will get 5.7057, which is in negative, and this is in kg. So to calculate the enthalpy change, this is the formula Q by N, and you have to use the moles of limiting reagent because you can see that here the 0.0500 moles of sulfuric acid are required for the complete neutralization, but you have excess moles of sulfuric acid. I mean, you have 1 times 75 by 1,000. Okay, so you have moles of sulfuric acid. They are 1 times 75 by 1,000 and they are 0.075. So moles of sulfuric acid required for the complete neutralization, they were 0.05. So that's why if we compare these two values, sulfuric acid is in excess. So you can't use either this mole or this mole. So you have to use the moles of sodium hydroxide. So minus 5.7057 and the moles of sulfuric acid were 0.1. So you will get minus 57.1 and then a unit is kg per mole. Then the next part is the reaction between sulfuric acid and barium hydroxide. So we'll get a barium sulfate if we do the double displacement reaction, barium with sulfate and hydrogen with OH, then we will get H2O, and this is the balanced equation. That if you put 2 here, you will get the balanced equation. So aqueous, aqueous, this is solid and this is liquid. So just why the enthalpy change of neutralization? This is the neutralization as well as the precipitation because you are getting the precipitate as well. So just why the enthalpy change of neutralization cannot be determined using the addition of dilute sulfuric acid to the aqueous barium hydroxide. Uh, if we react these two substances, you can see that we're getting the white precipitate of the barium sulfate as well. So precipitate of the barium sulfate also involve energy change. So that's why it is difficult to measure this. So the precipitate of barium sulfate also involves an energy change. So that's why it's difficult to measure the enthalpy change of neutralization by using this reaction because you are getting a precipitate and precipitate that is also formed. So that also involve energy change. So that's why it's very difficult. This precipitate is made up of Ba2 positive and SO4 2 negative ions, and they can. There is another concept in this, which is the lattice energy. So that's why lattice energy is not in the AS level. So it is not necessary to mention here. Just write that the precipitate of barium sulfate also involve an energy change. So that's why it is difficult to measure the enthalpy change of neutralization. This is up to the question number 2.